Hey aerospace students, let's talk about aircraft engines, their types, and their placements. Let's start by watching this video together.
Rolls-Royce is one of the world's leading engineering companies, designing and developing high-technology power solutions based on very efficient engines. These are used for applications on land, at sea, and in the air. Our engineering strength is built on two key technology platforms, the gas turbine and the piston engine. So how do they work? In the case of the gas turbine on an airliner, air is sucked in via the large front fan. The majority of the air is directed around the engine as pure thrust. The rest enters the engine and is squeezed through compressors consisting of a series of blades. Pressure increases at each stage as the air is squeezed. In the combustion chamber, the air is mixed with fuel and ignited. The hot air explosion is directed towards the back of the engine, generating more thrust and rotating the turbines, which in turn are linked to the front fan and compressors. A piston engine also operates by air being compressed and mixed with fuel. Air is drawn inside a cylinder, then compressed by a piston and mixed with either diesel or liquefied gas. As the mixture ignites, the energy created pushes the piston to the bottom of the cylinder. The piston then returns to the top in a continuous process. Rods connected to a crankshaft convert the vertical movement of the pistons into a rotating motion. As a result, the piston engine can power a wide range of applications: electrical generators, ships, vehicles, and railway locomotives. Efficient power on land, at sea, and in the air.
Earlier, you were asked to take a look at a presentation on your own, one about Newton's three laws of motions. Well, let's talk about exactly that, something you're probably more familiar with than you might think. More specifically, what those three laws are. As we go through this, think about how they could be described in your own words. His first law is that every object persists in its state of rest or uniform motion in a straight line unless it's compelled to change the state by forces impressed upon it. We often think of this as something's going to stay at rest or in motion unless something acts upon it that's an outside force. And then the second law we often think of as just being an equation, force equals mass times acceleration, or F equals ma. We can also substitute F for W, a weight, and we can think of A, or acceleration, as an acceleration due to gravity. So F equals ma can very easily become weight equals mass times gravity, or the acceleration due to gravity. And that can help us understand what this statement is that describes Newton's second law. Force is equal to the change in momentum per change in time. For a constant mass, force therefore is equal to mass times acceleration. His third law, however, is a little easier. If we think of the fact that every force has an equal and opposite reaction. So in other words, if I act upon an object with a force, so an action force has then some sort of equal and opposite reaction force. So I push on something, it pushes back. That's Newton's third law. What does thrust counteract? We know lift, we know weight, they counteract each other. But in an airplane, thrust counteracts drag, which you should be familiar with at this point. So let's talk about how we actually do that in an airplane. How do we counteract the thrust or the drag with the thrust? What do we do to generate enough thrust to counteract the drag of an airplane? This lesson will focus on propellers as well as on turbines. These propulsion systems are pretty common. There are also ramjets and scramjets, which is simply a supersonic combustion ramjet, And then we should probably mention, at least for context, rockets. All of these take air or oxygen and some type of fuel, combining them together and burning them. Chapter 5 of our textbook, which is called Propulsion Systems, It's a Matter of Energy. It's a clever title, I know. Is a fantastic resource for this lesson. I highly encourage you to look at it, at least look it over, if not read it. You never know where a quiz or a test question may come from. Chapter 5, Propulsion Systems, It's a Matter of Energy. When it comes to general commercial or most military aviation, there are two types of engine categories to consider: reciprocating and turbines. Now, reciprocating contains pistons and comes in two types: gasoline-powered 2-stroke or 4-stroke pistons, and diesel, which isn't typically used in aircraft. Turbines come in multiple types as well. You have turbojet, turbofan, turboprop, and an afterburning turbojet. And each of these images here are very simplified versions of them. It shows them with semi-cross sections of the cowling, with the compressor blades, the burning section, the one turbine at the back, and then some type of nozzle where the gas can be exhausted. With a turbofan, you have a fan in the front, and with a turboprop, you have a prop in the front. But in an afterburning turbojet, you have an afterburner that re-injects fuel into this already hot gas and expands it even more. More on those later. All engines, whether reciprocating or turbines, have 4 operations to them. These are the operations shown with a cross-section of a turbojet. Intake, where the fuel and air is brought into the engine, and compression, where we compress the air, and in the instance of a reciprocating engine, the fuel is already mixed in. And then we have a power section, which is where we combust the fuel-air mixture. In a jet engine, this is also where the fuel is introduced to the air and then burned. And then for the exhaust, gases have to come out of the engine, and in a jet engine like this turbojet, they move through the turbines. Oversimplified, we can think of this as suck the air in, squeeze it down, combust it or bang, also a lot of times referred to as burn and blow. Suck, squeeze, bang or burn and blow. Suck, squeeze, bang, blow. Suck, squeeze, burn, blow. If it's in a jet engine, burn makes more sense since the burning part of this is constantly happening. But in a reciprocating engine, it doesn't constantly burn. It is literally ignited with a piston reaching the top and a spark plug igniting the gas and pushing that piston back down. It doesn't happen constantly. It happens in a reciprocating cycle. Pistons can be broken down into 2 parts. They're referred to as a 2-stroke because there is a downstroke and then an upstroke in one revolution. And in that single revolution, you can see 4 operations: compression and ignition in the downstroke, followed by an exhaust and intake in the upstroke. 4 operations, 2 strokes, one down and back up. That's 1 revolution, 4 operations, 2 strokes. Notice that there's this similarity to a turbine engine, and there is still this intake stage, this compression stage, a power stage, an exhaust stage, and with reciprocating engines, it happens in cycles. 2 cycles allows for a compact design and therefore are used with smaller engines. They are more powerful, but they do waste more fuel. They can be very leaky and therefore not fuel efficient. They are also much louder than a 4. They're referred to as a 4-stroke because it takes 2 revolutions to move through all 4 operations, and this means it moves down and up twice. 1 operation for each stroke. These are the types of engines typically used in cars and small trucks as well as small aircraft. The physical one that you see shown on the left is a Lycoming engine, a common small general aviation engine. Its horizontally opposed reciprocating engine, known as a flat engine, is pretty common in something like a Cessna 172. The pistons are 180 degrees opposed from each other. Piston here, piston on this side. Piston here, piston on this side. You can find more information about various different types of reciprocating engines at animatedengines.com. Great website, by the way. So remember, compared to a 2-stroke, these are more fuel efficient and they are much quieter. This is an image of a Continental 6-cylinder horizontally opposed reciprocating engine that's been mounted in a small general aviation airplane. Students and I were able to see it undergoing maintenance in the hangar at the Henderson-Oxford Airport while on a field trip there. During the same field trip, we were able to see multiple airplanes while maintenance was being conducted. In this image, you can see a wider view of the plane's power plant along with the firewall and even fuel tanks in the wing. Here we see an engine that we'll zoom in on in a second, and its firewall connected to it with its truss, and you have fuel tanks in the wings. Let's take a closer look. You can actually see that truss right here mounted to the firewall and then mounted to the engine to hold it in place. This engine is very similar to the engine you saw on the previous 4-stroke engine slide. Pretty much the same thing. Let's watch this short video on how a 4-stroke engine works in real time.
Hey, it's me, Destin. Welcome back to Smarter Every Day. You've probably cranked a car engine thousands of times in your life, right? You're familiar with that roar as the engine comes to life? Have you ever thought about what's going on inside the engine? Think about it. You've got thousands of explosions happening every minute, and they all come together to make one unified sound. Well, today on Smarter Every Day, I want to learn what's going on in an individual cylinder. We kind of get a feel for how an explosion propagates inside of a combustion chamber with the transparent potato gun video, but for years, I wanted to see inside of a working engine. Today on Smarter Every Day, we're going to get to see this. Someone posted on the Smarter Every Day subreddit that there's a channel called 805 Road King that had created just this, a transparent engine. So I loaded up the high-speed camera and went to Cinnaminson, New Jersey to meet Everett. This looks like the right place. You Everett?
Destin!
Hey, what's up? I'm Destin.
Come on in. We're just getting your phone because my phones are out.
Hey, what's up? I'm Destin.
Come on in.
How's it going?
Pretty
Pleasure
good.
to meet you guys. Oh, dude, you have a jukebox.
You like that? In 1953.
That's awesome. That's awesome.
I'll let you take a picture of it later.
How you guys doing? Is this the shop?
This is it, man. It smells like...
Oh, it smells like freedom. This is Everett. He works with his buddy Mike to create all kinds of little mechanical marvels. Their specialty is taking apart a single-cylinder Briggs & Stratton engine from the 50s and converting them into all different types of things. For example, this one is turned into a hit-and-miss engine, which is really hard to do. This one is an absolute Frankenstein. They took 4 single-cylinder engines, chopped them up, and put them together to make one 4-cylinder engine that runs like a kitten. It's amazing.
The seam is actually right here.
And you welded that?
And here, yeah. There's a.
How did you weld 4 engines together and then have it aligned so a crankshaft could go in there?
It took a long time to do.
If you don't really appreciate what I'm saying here, just understand these guys are doing very difficult things with very crude tools. They're basically performing mechanical magic, which is why I wanted to see this. This is it, huh?
That is it.
I love it. On a normal Briggs & Stratton engine, the spark plug is right in the middle on the top of a cylinder and is fired by a magnet that moves past a coil. These guys moved the spark plug so you can see down into the engine and came up with a clever way to fire it with a buzz coil from the 1920s. They're also running the cylinder on propane instead of gasoline because it's cleaner and it makes the engine last longer. Now that we understand that this is basically a normal engine that they're taking the metal head off of and replaced with an acrylic head, it's time to get the high-speed camera set up and see the one thing I've been wanting to see for several years. An explosion inside the engine.
I can't tell you how excited I am about this this camera mount you built with its engine hoist.
It's like, this is the most acoustically pleasing thing I've seen in a while.
I just triggered it.
Okay, this is pretty and all, but I want to understand exactly what's happening. We have the piston on the left moving up and down inside the cylinder and two valves on the right. Let's take a look at how a four-stroke engine works and count off each of the four strokes along with me. The first thing that happens is one of the valves on the right opens, allowing a fuel-air mixture to be drawn into the cylinder. This stroke is called the intake. When the piston gets near the bottom of the cylinder, the intake valve closes and then the piston starts to compress the gas. This is called the compression stroke. The third stroke is the pretty one. This is called the power stroke. The explosion happens and increases the pressure inside the cylinder, which applies force to the face of the piston, pushing it down. When all those gases have burned after that third stroke, the exhaust valve then opens, and the fourth stroke, called the exhaust stroke, clears the cylinder of all those exhaust gases. The intake valve then opens back up and the process starts over and over again. Timing is everything in an engine to make sure it works properly. For example, you want to make sure the spark happens just before the piston is at top dead center because you want the pressure to be building up at the same time as that piston is ready to start moving back down. When you hear a person talk about the advancing or retarding of the timing of an engine, that spark timing is what they're talking about. If you look really closely, you can see that the spark happens just before the piston reaches the top of the stroke. I asked Everett and Mike if they would dare to run the engine on gasoline for me because I wanted to see a brighter flame. I was really excited when they said yes, and I was even more impressed when they said that they could change that engine over in just a matter of seconds.
So we're already converted? Like, you're done?
That's it.
That was fast. Man, that's good right there.
Okay, now that you know how an engine works, watch each of the four strokes and see if you can identify each one. Intake, compression, power, exhaust. Intake, compression, power, exhaust. Now think about the engine in your car. All the explosions are synchronized together to make that one constant engine roaring sound.
That was really awesome. So you got to see inside of an internal combustion reciprocating engine in real time. But there are various types of reciprocating engines that have been used in aircraft over the years. You saw the horizontally opposed type a little bit ago, but there are also inline engines, which were often air or water cooled, and inline engines were mounted so that the crankshaft was directly turning a propeller and all of the cylinders were mounted on the same side of the engine crankcase, one behind the other. Although this worked well for things like automobiles, it was often difficult to cool them with air as they blocked the airflow around the 3 back cylinders, leaving them to overheat pretty easily. This meant needing to water cool them, and that added unnecessary weight. This led to creating rotary engines. It was an inexpensive and lightweight alternative to inline engines in early aviation. Military purposes, though, demanded engines to have increased and better climbing and maneuverability performances, as well as improved reliability. With rotary engines, the pistons are arranged radially and uniformly spaced around the crankshaft. What was weird about them is that the crankshaft itself is bolted to the body of the airplane, while the entire engine crankcase is spun around with the propeller. Well, overheating was solved, but several other problems were created. There's a lot of mass spinning around, creating a gyroscopic effect on the aircraft. This made it tough to maneuver easily in flight. Oil would also pool in the cylinder heads as the RPMs were ramped up, and would literally fly out of the engine and splatter the pilot. This led to radial engines, which we'll talk about on the next slide, but before we get into those, let's discuss V-type engines. This type was around by the end of the 19th century and was actually used in aircraft early on, in fact 3 years after the Wright brothers' first flight. But mainstream use of them was not fully realized because those early designs were heavy and had a marginal horsepower. There was an increase, however, in their use as airplanes became more streamlined and as V-type engines began to have better horsepower to weight ratios. This type of engine was pretty popular with the very sleek racing type of airplanes, as well as highly used in fighter aircraft during World War II. Well, this brings us to radial engines, which we see one shown in the top left corner. It's from the Spruce Goose, which is on display at the Evergreen Aviation and Space Museum in McMinnville, Oregon. If you've never looked up or don't know what the Spruce Goose is, it's quite an airplane. You should look it up. There's some videos that you can find online about it. This shows how the engines look when they're inside the cowling. That's the device that goes around the engine. We can see it here in the imagery. This helps reduce the drag of the large frontal area of a typical radial engine. More information about the museum and this airplane can be found at evergreenmuseum.org. The remaining engines across the top, here and here, and in the bottom right corner, are on display at the Smithsonian Air and Space Museum Udvar-Hazy Center. The image in the center, right here, is of a Pratt & Whitney Hornet R-1860-B 9-cylinder radial engine. It's from 1929. The top right image is a 5,000 horsepower Lycoming CR-7755-3 radial engine from 1946. It has a whopping 36 cylinders total. At first look, radial engines seem similar to a rotary engine, but internally they are quite different. The crankcase is mounted to the airframe. The crankshaft and propeller are the only rotating objects, which solves the whole rotating mass issue that we saw with rotary engines. There is always an odd number of pistons, and only one is the master piston to which the other pistons are attached. These engines are not very streamlined though, but do have uniform cooling for all cylinders, though it wasn't perfect. Later, stacks of cylinders were incorporated you can see that here. We slightly rotated each set of pistons so they could still get some even cooling. In the bottom right corner, you can see a video of a 9-cylinder radial engine in action. This display at the museum shows the engine split open and reveals a cross-sectional view and shows just how the pistons work together. In the bottom left-hand corner is a video explaining this process in a bit more detail. Let's look at how a radial engine works.
It's Oshkosh Week, and if you take a look at the flight line, you'll find a ton of World War II bombers and transports, and almost all of them are powered by radial engines, which leads us to a question we got last week. How does a radial engine work? And the answer is just about like every other reciprocating engine. It follows a 4-stroke cycle. The first stroke is the intake stroke, and that's where the downward moving piston sucks the fuel-air mixture through the intake manifold and the intake valve. Then, as the piston begins to move up, it compresses that mixture in the compression stroke. Right before the piston hits the very top, the spark plugs fire, and those sparks start burning the fuel-air mixture, causing the gases to expand and forcing the piston back down in the power stroke. And then the crankshaft starts spinning the piston back up to the top, forcing out the burned fuel-air mixture in the exhaust stroke. If you're looking at a radial engine from behind, as you would from the pilot seat, you'll find that the cylinders are numbered in clockwise order. So on this engine, they'd be numbered 1, 2, 3, 4, and 5. And a radial engine follows a very specific firing order. Here, you alternate cylinders. So it would be 1, 3, 5, 2, and 4. Radial engines were used because they could generate a lot of power, and they were really, really simple. They had very short crankshafts, which could be very, very strong because you really didn't need a lot of length between your prop and your cylinders. And you could fit up to 9 cylinders around your crankshaft. However, as time went on, 9 cylinders didn't give you enough power, so we started to add more and more rows of cylinders. In fact, the Wasp Major had 4 rows of 7 cylinders for a total of 28 cylinders. It was used on the B-36 Peacemaker, which had 6 Wasp Majors pushing propellers and 4 turbojet engines. The slogan was originally 6 turning and 4 burning, but the Wasp Major had a problem. It didn't cool really well. As the air moved past the first row of cylinders, it did a great job, but it got warm, and so each successive row of cylinders was less efficient to cooling, and the Wasp Major had a tendency to catch on fire. So crews gave it a new nickname: 2 turning, 2 burning, 2 smoking, 2 choking, and 2 more unaccounted for. At the end of the day, turbojets replaced the radial-powered piston engines simply because they were much more reliable and they could generate a ton more horsepower. But that's a lesson for another day.
So we had inline engines. They overheated. We had to put water in them. That became heavy, so they're inefficient. So then we turned to maybe some V6 engines, but they were less efficient and not very light, and the aircraft weren't streamlined enough yet for them. So we moved to rotary. We spun the engine's crankcase, and this just flung fluids everywhere. So to get rid of that issue, we moved to something similar to that, but now we didn't spin the engine, which is probably a good idea. That didn't produce in the end enough power. 9 pistons, yeah, they were cooled easily because the air could flow past all of them, but not enough power, which meant stacking them and then rotating each stack slightly, trying to provide enough air movement around them to cool them. But in the end, as you see with this giant Lycoming engine here, it's not doing the job, and they would overheat. Okay, so where do we go from there? Well, we should talk about some jet engines, but before we do, let's talk about carburetors. So as we finish up talking about reciprocating engines, let's talk about something that was used to mix fuel and air. It can be done with a carburetor. Carburetors reduce the area that air has to pass through, which creates a vacuum as the speed of air increases and the pressure decreases. This vacuum then sucks in the fuel, mixing it with the air, and all of this is thanks to, you guessed it, Bernoulli. His law shown here with static pressure and density and velocity, which is also known as the Venturi effect. And of course, if you're interested in this, you can find more information about this on NASA's GRC website. Keep in mind that carburetors are only used with gasoline engines and when we don't have fuel injectors, which we have nowadays. It's actually pretty common. So big takeaways here: carburetors reduce that cross-sectional area as air passes through it, and this creates a Venturi effect that allows a vacuum to pull the fuel in, mixing it with the air. Icing, however, can be a problem for carburetors, so the switch to fuel injection, at least for airplanes, was mostly because of icing. Although the heated air from engines could prevent icing, it was not 100% effective. So again, the big deal here and why we switched from carburetors to fuel injection is because of icing. And this could have been prevented with, at least to some degree, heat from the engine. It wasn't 100% effective, so we had to find a solution, and in the end that was fuel injection. Now, engine operation in a reciprocating engine is very similar to the operation in sections of a turbine engine. This is a turbofan, probably on a military aircraft, at least a simplified cross-sectional version of it. You have a fan at the front with a low bypass ratio, so not like on a commercial jet. And then there's the compression section. Well, this fan and compression section are the intake area. As we intake it into the compression, it's much like how we're pulling air and fuel mixture in and then compressing it up. And then we have the ignition section, and then we have the exhaust and expansion. As the air expands, because it's been heated, it moves through turbines in a jet engine. Here in a typical reciprocating engine, we have compressed the air, ignited the air, pushing the piston back down, and then we push that expanded air back out through the exhaust port. So similar, but not exactly the same. Turbojets are the simplest and earliest type of turbine engines. As seen in this highly simplified GIF below, large amounts of surrounding air are continuously brought into the engine inlet, shown here with these red lines. In England, they call this part the intake, which is probably a more accurate description since the compressor pulls air into the engine. We have shown here a tube-shaped inlet, like one you might see on an airliner, but inlets come in many shapes and sizes, depending on the aircraft's mission. At the rear of the inlet, the air enters the compressor. The compressor acts like many rows of small airfoils, with each row producing a small jump in pressure. A compressor is like an electric fan, and therefore we must supply energy to the compressor. At the exit of the compressor, the air is at a much higher pressure than free stream. In the burner, aka the power or combustion section, a small amount of fuel is combined with the air and it's ignited. In a typical jet engine, about 100 pounds of air per second is combined with only around 2 pounds of fuel per second. Most of the hot exhaust has come from the surrounding air. Once the hot exhaust leaves the burner, it is passed through the turbines, and the turbines work like a windmill. Instead of needing energy to turn the blades to make the air flow, the turbine extracts energy from a flow of gas by making the blades spin in the flow. In a jet engine, we use the energy extracted by the turbine to turn the compressor by linking the compressor and the turbine by a central shaft. The turbine takes some energy out of the hot gas or hot exhaust but the flow exiting the turbine is at a higher pressure and temperature than the free stream flow outside of the engine. Because the exit velocity is greater than the free stream velocity, thrust is created as described by thrust equations. For a jet engine, the exit mass flow, let me say that again, for a jet engine, the exit mass flow is nearly equal to the free stream mass flow. Since very little fuel is added to the stream, the amount of mass flow is usually set by flow choking in the nozzle throat. Now, that is a lot of information, which we can break down a little later. Just remember this: a jet engine sucks in air, the air is compressed. It does this with spinning airfoils and stator vanes and decreases the cross-sectional area. The compressed air mixes with fuel and is burned. This causes an expansion of the air, increasing its speed, which then passes through a turbine that is used to remove energy from the fast-moving air. Pulls it in, compresses it down, expands it by igniting it, pushing it through some turbines that spin like a windmill that are connected to a shaft that go back to the front of the engine and spin the compressor blades. Suck, squeeze, bang, and blow through those turbines and out the back of the engine to give it some thrust. Okay. Let's break down the operations in parts just a bit further. Throughout any gas turbine, there is an interchange of pressure and velocity. In a compressor blade passages, air slows down and pressure increases. In turbine blade passages, gas accelerates in response to a reducing pressure. The fundamental operation of the gas turbine can be explained in two ways: as an energy conversion process, or more fundamentally in terms of Newton's laws of motion. The energy explanation states that the energy input in the combustor provides the turbine gas with enough energy to drive the compressor and accelerate a jet or drive the power turbine. But energy explanations are shorthand. An energy balance does not explain the mechanism that is working. The mechanistic explanation is that a cold gas is less bulky than a hot gas at any given flow, velocity, pressure, and mass flow. A cold gas has a smaller flow area than a hot gas. The braking force on it is, as it passes through a compressor, is low for a given rise in that pressure. In contrast, the accelerating force of the hot gas in a turbine is high for a given drop in pressure. So we're talking about all these different pressure changes. We compress the air down and we ignite it and we push it by it being expanded through low and high pressure turbines. All right. Given that the change in velocity in a matched compressor and turbine, so in other words, the fact that the compressor and turbine are connected, you have to give a balanced rate of change of momentum and torque. The result is that the turbines drive the compressors for less pressure drop than the compression pressure rise. So the compressor can create a higher pressure that then gets burned and pushed this bulky gas instead of this cold gas through the turbines that can then create the movement that the compressor blades need to then compress more air that gets burned and pushed through the blades in the turbines. Long story short, there is a series of low pressure turbines, LPTs, and high pressure turbines, HPTs, because there is a difference in pressures and there must be a balanced rate in momentum and torque changes, spare pressure is left over to be used elsewhere. For example, leaving the engine instead of turning compressor blades. That's a lot of information. Take a moment, go back over it if you need to, rewind the video. Okay, hopefully you have a little bit better understanding of that. Here's an exploded view showing those components. The nozzle at the end, a very simplified version of what a turbine might look like. It's connecting a shaft through that burner section and back into the compressor section, which then turns these blades. And of course, here in the middle of that shaft is the burner section, as you've seen in some of the animations that we've provided. This is an SR-71 commonly known as the Blackbird. Again, this is at the Udvar Hazy Center. This is a picture that I took while there on vacation. This plane is designed to travel at both subsonic and supersonic speeds using the same engines. It is a very unique design, and it transforms from a typical turbojet to a modified ramjet. And here you can see that the wing, this delta wing, has been lifted up to reveal some of the internal workings of this jet engine. Not to be outdone, though, by the incredibly expensive and complicated F-35 jet engine. You can see the F-35 in the image in the background here. This is just a little bit further down in the museum from that SR-71. As you can see from the vector adjusting nozzle on the left and the engine that would be placed in the midsection, this aircraft is designed for vertical takeoff and hovering capabilities. So we basically can create a VTOL here. You have your typical turbojet engine. Its nozzle can be redirected to rotate down 90 degrees, and then it has its shaft connecting past the turbine, past the compressor of the turbine to another engine that is here in the midsection of the airplane, redirecting air down to keep it balanced front to back when it's in this hovering configuration. Very complex, very difficult airplane to fly, my understanding of it. Let's talk about the next type, which is a turbofan. This engine is the most common variation of the gas turbine engines, at least the basic gas turbine engines. As with other gas turbines, there is a core engine. We see it here in this GIF. In a turbofan, the core engine is surrounded by a fan in the front and an additional turbine at the rear. Okay, so we have the turbine that spins the compressor, and then you have a series of turbines that can spin the turbofan, or the fan at the front of the turbofan. The fan and the fan turbine are composed of many blades, like the core compressor and the core turbine, and are connected by an additional shaft, which is also called turbomachinery. The fan shaft passes through the core shaft for mechanical reasons. So you have a shaft that connects the turbine for the compressor, and then inside of that one you have another shaft that goes from further back in the engine all the way through up to the fan. This type of arrangement is called a two-spool engine, one spool for the fan and one spool for the core. Some advanced engines have additional spools for sections of the compressor, which provide for even higher compressor efficiency. So how does a turbofan engine work? The incoming air is captured by the engine inlet. Two air streams are what are created. Some of the incoming air, we see that colored red on the figure, pass through the fan and continue on into the core compressor and then into the burner, where it is mixed with fuel and combustion occurs. The hot exhaust passes through the core and fan turbines and then out the nozzle as in a basic turbojet. The remaining air that passes through the fan, colored blue here, bypasses the core, goes around it, inside of the cowling, but around the core, and provides a significant amount of thrust. The ratio of the two airstreams is known as the bypass ratio. And of course, the GRC NASA website has a whole lot more information to include a crazy looking GIF like this. This page is pretty simple. There's a link here that you can get to if you download this PowerPoint. It's a great resource that shows the stages of a turbofan. We're not going to look at it in this video, but it is pretty complex. You can look at each individual stage and even break down those stages further. There's usually somebody that talks to you, kind of like I'm doing in this video, and breaks you down through a basic fly-through of these. I highly, highly, highly recommend that you check this out. It is super detailed and gives you lots of really good information. Okay, so what's the purpose then, if we're looking at a turbofan, for that white stripe? Sometimes we see it as a spiral, sometimes it looks like a comma, sometimes, depending on where you are and what the airplanes are, they look like various different shapes that spin. What is the purpose of that? The answer is all about the personnel that's on the ground. They need to know whether this engine is turning or if it's static. Let's hear from Captain Joe. He's got a lot of good information on this. Captain Joe?
Dear friends and followers, welcome back to my channel for a short video about the little swirl you can see on most jet turbine engines. Now once they spin, they look pretty cool, but do they have a specific purpose? And you'll be surprised how many different shapes and sizes are out there. So let's get spinning.
1383, runway 27, clear takeoff. And that is 1538, runway 27, -20.
Now let's imagine you're sitting in a terminal, gazing out of the window, and the incoming aircraft is taxiing towards the gate position. I'm sure you've spotted these before, which look like one of those spinning things fortune tellers use to mesmerize their clients. Obviously that's not their purpose, and alongside the fact that they don't have an industrial name. So let's call them spinner spirals for today's video. Now the spinner itself is an aerodynamically shaped cone or dome in the center of the fan, covering the fan blade mounts. Many engine manufacturers like Pratt & Whitney, General Electric, CFM and Rolls-Royce have been painting spinners with the catchy swirls for decades. The practice even goes back as far as World War II, when the spirals were painted on the propeller cones. So the primary reason for painting designs on engine spinners is for safety of the ground personnel. Now working near a running jet engine is extremely dangerous, and for example a Boeing 737 engine running at idle power has a hazard zone of 9 feet to the front and the sides of the engine. Now this means that even at idle thrust, a human that walks within the hazard area or any loose objects risk being sucked up into the engine. And when the engine is above idle thrust, the hazard zone increases to 14 feet or more. Now, not to speak of even larger hazardous zones of a Boeing 777, for example. Therefore, it's absolutely critical that the ground personnel can identify a running engine and stay away from it. Even though jet engines are incredibly loud, a running engine may not be obvious to ground personnel. Airport aprons often have several airplanes in close proximity with engines screaming next to each other. Therefore, ground personnel have to wear hearing protection to suppress the deafening noise. And making matters worse, it can be hard to see that the engine is running, especially during nighttime operation, as the black and grey fan blades become translucent when they're spinning. Therefore, spinning spirals make it a lot easier to identify a running engine. And besides that, ground personnel can check if the airplane's red anti-collision light is still flashing. This indicates that the pilots have received a startup clearance and will start the engines very soon. and on arrival at the gate the light is turned off by the pilots after the engines are shut off and spiral down, after which it is safe to approach the engines from either side. For the same safety reason, the tips of propeller blades on propeller-driven airplanes like the Dash Q400 are painted in bright colors to be more visible to the human eye. And you won't believe how many incidents have happened in the past involving jet engines and ground personnel. Do the spirals scare away birds? Now that's a difficult question to answer, and many rumors have arisen around this question. Birds and aircraft engines are a bad combination. Bird ingestion and bird impact cause expensive damage to the engines, and the birds aren't happy about it either. For years it's been speculated that spinner spirals might startle or frighten birds away from the engine during taxi, takeoff and landing. Doing the research on this topic, I found numerous explanations that made sense in my opinion. However, I'm not an ornithologist, but birds have the tendency to seek shelter in holes and caves. A spinning turbine imitates a black hole, so birds may be more likely to fly towards them. Therefore, the flickering image of the spiral startles the birds to fly near the engine inlet. Japan's All Nippon Airways (ANA), for example, completed a year-long study in 1986. The airline patented wobbly ball-styled eyes on the engine spinners of some of the aircraft. The airline found a small reduction in bird impacts on those airplanes, so ANA added the markings to the rest of their fleet. If you consider the cost of a $40 spinner paint job compared to a $10 million engine replacement, you would have all the spinners painted if you thought it would be even only a minor reduction in bird strikes. This has then led to many different shapes and styles that engineers and airlines have tested on their planes. Here, for example, you see the apostrophe on the Boeing 747-400 by Cathay Pacific, the most common one, the G-swirl on a Boeing 777 by Emirates, the longer spiral on a Singapore Boeing 777, the typhoon or hurricane on the Philippine Airlines Airbus A330, and a few more which were really hard to find, the horseshoe, the wobbly crescent and the comma. I personally think they look cool, and I like them for their safety benefit for the ground personnel, as their job is dangerous enough. I can't really say if they straddle birds or not. I've experienced numerous bird strikes with spinner spirals and without. I personally think the most effective way to scare birds are with the landing lights or by the airport ranger who fires a shotgun every now and then to scare the birds. I'm not kidding, they really do that.
Okay, well, that's it for this video for now. There is still more to this presentation, but after we have a chance to go over some more of it in class, I will post another part to this so that you have a chance to go back and look at it.